Hello and welcome to this ISTEC distinguished lecture for this morning. For those of you who don't know, ISTEC is the Information Science and Technology Center here at CSU, where we deal with all matters related to information sciences and technologies on campus, ranging from research, education, outreach, and industrial connections. We're very fortunate today to have a very distinguished lecturer as our ISTEC distinguished lecturer for today, Professor Sanjeev Kulkarni. Professor Kulkarni got his PhD in electrical engineering and computer science from MIT, and then spent a little bit of time at Lincoln Labs, right? Since 1991, he's been at Princeton University, where he's a professor of electrical computer engineering and dean of the graduate school at Princeton. Professor Kulkarni is a distinguished researcher in several different areas, including information theory, signal processing, and related areas, and an award-winning teacher as well, very well known for his captivating style in class, really very popular. So I hope you'll help me today to welcome our speaker speaking on machine learning and democracy, Professor Sanjeev Kulkarni.
Thanks, Edwin. Thanks so much for the kind introduction. Thanks for the invitation. It's really great to be here. Really appreciate all of you being here as well. I wanted to talk about, as Edwin said, machine learning and democracy. I'm going to spend actually a little bit of time. I'm probably preaching to the choir, but wanted to just spend a little bit of time on the science of information meets the liberal arts, a bit of a tour of AI, which many of you may be familiar with, but I thought it's worth talking about that some to bring us up to machine learning. And then the problems that I've been interested in recently all have a similar flavor, and wanted to mention two of them. In fact, this afternoon I'll talk more about the second one, aggregating probability judgments, but really want to get to the voting theory and social choice, which is the connection to democracy and the type of problem and the approach that we're interested in is what the connection to machine learning is. So first, preaching to the choir. I actually talk about this and use sort of a similar diagram when I was teaching. I haven't been teaching it for a few years, but I was teaching for many years the first course in electrical engineering at Princeton, which is in an introduction to signals and systems. But meant to be a very introductory perspective. And in fact, the way I tried to teach it brought in students from all over campus. In fact, at one point, I think only about half the class was actually electrical engineers. And the rest of the class were some other engineers, but actually many students from the liberal arts as well. And I actually feel very strongly about this paradigm of the way we think about systems and why information processing or information sciences is that critical in almost everything we do today. And the way I try to explain that paradigm is that these days, because of the power of information processing and computing, the paradigm for designing system, almost no matter what it's going to do, is really to convert whatever you're trying to measure into data, information, signals, do all the processing, the computation, and then send back the data, information, or signals to actuators. And the important thing is that for a wide range of applications, by designing the right sensors and actuators, you can then convert everything almost to, if you will, an information processing task. And the systems can be very complex, they can be dynamic, they can be distributed, but it's really the this general paradigm that has focused so much attention on this back end and not just trying to design a particular system for a particular application, but actually trying to focus on some of the fundamental problems within information processing as problems in and of themselves. And that's why they often fall into electrical engineering or computer science, is because the information processing is carried out by electrical means, by fundamental devices based on electricity and magnetism and so on, which is why all of these different areas fall under or are studied as problems in and of themselves within electrical engineering and computer science. But, and in particular, learning and inference often is as well. But the way I try and explain it to the students in my class is that these basic problems in information processing have connections to many other areas. I've listed a bunch here. And so it's pervasive, connected to many areas, and I think we're at a place where, and again, I'm probably preaching to the choir, but for certain academic disciplines, I feel it's important to actually say it, that a liberal arts education, I think now, has to include some aspect, not just of understanding, some basic understanding of technology, but importantly, information technology. And I've done teaching and research at sort of the intersection of a variety of these fields, and in different ways. In some cases, they're inherently blended fields. An example of that is a course I teach with someone in the philosophy department at Princeton on learning theory and epistemology, which really blends topics from machine learning and inference, how we know what we know, or how we're justified in making inferences with topics in philosophy, but also courses that address the particular technology in a broader context. A course I taught for a while is one that Vince Poor, former Dean of Engineering at Princeton, introduced, called the Wireless Revolution. And then, of course, in research, there are similar problems, which is what I'm going to talk about with the voting theory, that share ideas and tools. So I think there really is a blending of problems in many of these areas with information technology. So I think a center like ISTEC is actually very timely and important. So after that pitch, AI and machine learning. So AI had its start around the 1950s, as I'll say in a minute, but AI, is, all of you probably know, is sort of the science of and engineering of making intelligent machines, and especially intelligent computer programs, but there's no real good satisfactory definition of what intelligence is, although we all have a sense from sci-fi movies, and you probably recognize most of these. But we don't have a good concrete definition of AI, but we all have a sense of some of the problems that are studied within AI. I've mentioned a bunch here, and in particular, the one I'll focus on is machine learning. Modern beginning, Alan Turing, actually in 1950 proposed the Turing test as sort of a way to assess intelligence. And things really started to take off in 1956 after this so-called Dartmouth conference, where they proposed this. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. And there were the golden years that followed that. In fact, there's a lot of excitement and enthusiasm. In fact, these bold predictions, so much enthusiasm and optimism that there were these predictions back in, well, this one from Simon back in 1965, that machines will be capable within 20 years of doing any work a human can do. Minsky, 67, within a generation, the problem of creating AI will be substantially solved. And then it gets even more optimistic. 3 years later, Minsky says, in from 3 to 8 years, so that would have been in the 70s, we will have a machine with the general intelligence of an average human being. And a lot of enthusiasm, and then reality started setting in. And the reality started setting in because as researchers tried to address certain fundamental problems in all of those areas, but one in particular, natural language processing, was studied quite a bit at that time, turned out to be an extremely hard problem. And so here's just an example of the types of difficulties that happen. So take a phrase, an English phrase, the spirit is willing, but the flesh is weak, and think about natural language processing. Well, in 2005, I actually tried this. So by the way I did this is take this phrase, translate it into, in this case, Spanish, and then translate the result back to English to see what we get. And if it works well, you should get the same phrase back again, but we got the alcohol is arranged, but the meat is weak. In 2010, you get this spirit is willing, but beyond their grasp. And this is an urban legend, but I think a humorous one. Going to Russian and back, the vodka is good, but the meat is rotten. I have to say, I've tried it now. If you just go to Google Translate, you try this, and it's gotten a lot better. And a lot of the reason, I don't work in natural language processing, but a lot of the reason it got better was the approach shifted from a very rule-based approach back in the early days now to real machine learning-based approaches. They've made incredible advances. So in fact, when I just tried it a few days ago, there's almost any language that I tried in Google Translate actually came out fine. Now, maybe I should have tried other phrases and so on, more complicated phrases, but at least the progress that's been made just in the last 10 years or so, it's quite impressive. There are probably two other urban legends. But you can see the difficulty that might come up in natural language processing. So anyway, the difficulties of some of these tasks led to disillusionment, and the so-called AI winter from the mid-70s to the about 1980 set in, funding evaporated, and a lot of effort went into other areas. By the way, I should have said this at the beginning. Feel free to ask questions at any time. I'm happy to make this a bit of a conversation as well. So an AI winter set in, but then around 1980, there was another boom in AI, and it really was a result of a focus on expert systems, really looking at problems in very specific domains, trying to extract what we know about the problems in those domains and construct systems for very special purpose applications. There's also this connectionist revival, sort of the first, maybe the second. There was a neural net enthusiasm much earlier, but there was a connectionist revival in the 80s with training algorithms like backpropagation emerged at that time. In fact, this was right when I was doing my graduate work at MIT, so I was sort of caught up in a bit of this connectionist revival at the time. Funding returned. In fact, a lot of it went to neural nets at the time, but other areas of AI as well. But then there's another bit of a winter, not quite as devastating as the first one perhaps, but these expert systems were expensive, they were brittle, they didn't work as well as one would have hoped. Basically, the expectations, again, were a little overly optimistic, and the community failed to sort of meet those expectations, sort of went into another winter, I would say. But we're now in another boom. In fact, I would say from the 90s to now, and it's going on, it's another boom, and the shift is really to machine learning. And the idea of machine learning, as you know, is to develop methods to automatically draw inferences from a wide variety of data. Data can come in many different types, different structures, all sorts of applications. And there are fundamental questions, both about developing algorithms for specific applications, as well as fundamental questions about what are the limits of learning, what can be learned, what can't, how much data do we need, and so on. And what's happened, I think, to drive this latest boom in machine learning is that we've just had incredible advances in a couple areas. One is computing power is a huge one. Things that we just couldn't do, impractical to do computationally before, are now feasible. Drawing on many more tools from a wide variety of areas. But another really important one is this third bullet, that we've actually transitioned from a mode where there was too little data for learning. That is, we couldn't draw the right inferences because we didn't have enough training data to the system, to actually the other problem, which is a problem of a different sort, where there's almost too much data. And the question is how to extract the relevant data and not have methods fall prey to not maybe fitting on data that's irrelevant, if you will. And we've had notable successes, and these, anyone recognize these? Yeah, Watson. Yep, Deep Blue, and then the DARPA Grand Challenge. So Deep Blue versus Kasparov. This was a while ago, 97. 6 games. You see the results, and Deep Blue won. DARPA Grand Challenge in 2005, and now we've come a long way from there with Tesla, and there's probably cars out on the road in Fort Collins, maybe, drawing themselves. And then Watson in Jeopardy. And Watson was actually a good example of a lot of the work in language, if you will. And so, tremendous progress over the past 50 years. We are in a boom. It's really, I would say, the machine learning boom now. It doesn't look like it's going to be abating. So I don't see a winter on the horizon. But we're still nowhere near the original promise of AI. Talk about this, connections to other fields. Let me sort of move on to an area that I'm interested in within machine learning, and that's collective decision making. And what I mean by that is there are many problems in machine learning where one agent has all the data. It's all centralized, if you will. The data is all in one agent. That agent is tasked with making inferences on a given problem. There are many other problems where the data, where there are many agents, a collection of agents, and the data is distributed. There might be other constraints as well, but each agent has some piece of the data that's important. It might be a belief, it might be a preference, it might be some measurements of the environment, and the data is naturally distributed, often distributed if you have many agents. It's often dynamic. It often comes in different forms. There's often resource constraints, whether it's time, bandwidth, power, constraints for communication between the agents. And somehow we want to aggregate the data from many agents, each with some partial information, draw inferences that aggregate the data and make a joint decision among the agents. And there are these, this is from another movie, I can't actually remember what, but with mobile sensors, smart dust was all the rage for a while. But there are many cases now where problems fall into this type, and some that you might not think of as sort of normally falling into that type, but recommender systems is actually one problem that I'm interested in that does fall in that type. With the advent of the internet, there's a huge amount of data, many individuals, many items, and we'd like to find a way to recommend items to new users. So the way you might think about it is that you have thousands of users, tens of thousands of users, maybe millions of users, and you have thousands of items, and a particular user maybe recommends, gives their rating on some subset, and usually it's a very small subset of the available items, and it's a small subset of users. So you have this matrix of user item preferences, which is extraordinarily sparse, and yet we want to be able to make inferences or predictions on how will a particular user rate a particular item. And that falls in this category. It's a machine learning type or inference type of problem where we're aggregating preference information in this case. And there are a lot of problems in recommender systems, and there's a lot of interest in there still is interest in this area. Issues of scalability as the number of users and items grows. Sparsity is a real problem. You have very little data, but you want to make good predictions. And there are these other problems. Cold start problem. When a new user enters the system, you have no data on that user at all. Maybe no shopping history or history of what movies they've even watched, much less rating information. How do we even start to make inferences for new users? There are attacks, as you probably know. You go on Amazon and there are all sorts of reviews, either sort of torpedoing a particular product or rating it very highly. How do you make inferences about which of the reviews, if you will, are genuine and which are attacks? So a lot of problems in this area. Very important area, one that I'm interested in, but it falls in this aggregation problem. A second area I'm interested in, and I guess that's what I'll be talking about more this afternoon, is another problem where you have agents, it could be humans, it could be sensors, and they each have probability forecasts on a bunch of events. And the forecasts are likely going to disagree. The sensors may observe different things, or the human judges or experts may have expertise in different domains. They may have different beliefs. They all give their probability forecast on many events that are complicated and logically complex, if you will. And what we'd like to do is take all of this information, these probability forecasts, and aggregate them and come up with a better estimate of the probabilities for different events happening. And the third problem area that, again, falls into this aggregation type of problem is voting and social choice. And that's what I want to spend most of the time now, the rest of the time talking about. And so voting and social choice, we usually don't think about machine learning techniques applied to it, and often there's not much to do if there's just two alternatives. So if you have two alternatives that you're deciding between, really there's nothing more to do than a majority vote. And so this is a case of aggregating preferences, where you have many individuals, and this is sort of a different regime from recommender system. Here we have lots of individuals, millions of individuals, usually a very limited set of choices. If you have two, there's not much you can do. But as soon as you have more than two choices, actually things get quite complicated, surprisingly so. And so here's one example of aggregating judgments, if you will, where things get complicated. It's not voting, but it falls under sort of a similar type of problem. So I don't know what that is. It's late night editing. The extra cue. So what this is supposed to be is, imagine the following: you have three judges, and you have the statement P, an individual committed a certain act. You have another statement, P implies Q, which is if an individual commits the act, then they should receive a particular punishment. And then you have the statement Q, the individual should receive a particular punishment. So what can happen is you have the first judge that thinks, yes, the individual committed the act, believes that if the individual committed the act, they should receive that punishment, and yes, they should receive that punishment. So they're logically consistent. Judge 2 is also logically consistent. They just don't believe the individual committed the act, but they do believe that if in fact they did commit the act, that they ought to receive the punishment. But because they don't believe the individual committed it, they don't think the individual should be punished. And likewise, Judge 3 is logically consistent, believes the individual committed the act, doesn't actually agree with the implication that if they did that, then they should be punished, and therefore doesn't think they should be punished. But you take a majority vote, which is the obvious thing you do in sort of voting with just two alternatives. In this case, it's sort of a set of interrelated logical statements. You take the majority, and the majority believes individual committed the act, the majority believes this implication, and yet the majority believes that the individual shouldn't be punished. As soon as you get more complicated scenarios with individuals, you can't actually apply majority vote and have consistent judges, if you will, lead to consistent outcomes with majority voting. So there are real questions about what we do in this case if things are even more complicated with more basic statements and more logical interrelations between them. How should we come up with inferences there? Here's a second example along the same lines, where a town is trying to decide whether they should build a new road. And two critical questions are, would a new road be helpful, and are there funds available? And let's imagine that 20% of the population says yes, a new road would be helpful, yes, funds are available. 40% think yes, it would be helpful, but we don't have the money. And another 40 think that we have the money, but it's not a worthwhile way to spend it. You take the majority vote, and it's going to pass. 60% sort of agree with each statement, and yet if you set the agenda differently and you just ask, should you build a new road, this 20 says yes, these two different groups of 40% both say no for different reasons, but they both say no, and the result in this case then is the road doesn't get built, actually by a wide margin. And so the interesting thing here, again, is because of the complexity of the choices available, it's actually quite interesting when you are thinking of referendums that the agenda, how the agenda is structured can make an important difference on the outcome. And so I think trying to understand these problems is actually critical to these cases where we're hoping to sort of assess the collective will of the people and decide on a direction. You have to give thought to these types of things. So more classical voting, and that's what I'm going to focus on now, similar things can happen as soon as you have more than two candidates. So this is very timely now. I had different names before. But let's assume, for the sake of simplicity, we have the population is described in this way, that 45% rank ordered the four candidates in this way. Clinton first choice, then Stein, then Johnson, then Trump. 40% rank it this way, and then 15% rank it that way. Yeah, please. That's right. Yes, and that's just for simplicity of the examples, but in fact, so even here, let's talk about this. There are 4 factorial per different rank orders that the population could have, and we're assuming the population somehow magically only has these 3. And that's just for the simplicity of this example. So you can see how complicated things are even with such a simple example. But we'll get to some real data where things actually get more complicated later. So the point is that it's rare that it's going to be like this. There's probably some that put Trump first, then Clinton right behind Trump, which is probably not likely, or vice versa, and then the other two. But there could be. And so we actually have many more permutations possible, and that makes things even more complicated. But even with this simple example, let's see how complicated things get. So the question is, how should we decide which candidate wins if the people actually had these as their true preferences? Yes. Well, in fact, we will. That's actually true. But in fact, we'll talk about how you might rig an election or what we might do to avoid rigging, and not so much rigging, but being strategic, because there are issues of not voting one's true preference, which we'll get to in a minute. But yes, no rigging here. So what we currently do is plurality voting. And basically what we do is look at the first choice, and that's it. We don't consider any other information. And you just look at the first choice candidate, and based on this, the first choice, we get Clinton gets 45%, Trump 40%, Johnson 15%, and we just pick the candidate that got the most first choice votes, and Clinton wins. And that's what we currently do. In fact, we don't even gather this other information. We only gather this first choice vote, if you will. That's one way to do it. But what about another way to do it? So there's something called instant runoff voting. And the idea of instant runoff voting is what we're going to do is we're going to successively eliminate the candidate with the fewest first choice votes. And so here, the first thing that we do is nobody put Stein first in this example. So we eliminate Stein. And then we look at the remaining candidates on the slate after Stein is removed and see who now has the fewest first choice. Well, nothing changed in the first choice, so it's still 45, 40, and 15. So the next person we eliminate is Johnson. And now there's only two candidates, and what we do is look at the remaining two candidates and see who has the most first choice votes among those candidates. Well, now what happened is we're now at a place where with just these remaining candidates, actually Trump has the most first choice votes. Trump now has 55 to Clinton's 45, so we eliminate Clinton and Trump wins. So different outcome with a different way of combining votes. Well, let's try another one. So another way of voting is something called board account. And the idea of board account is you assign points to rank positions. So first place you get 4 points, second place you get 3 points, third place 2, and fourth place 1 point. And you would, if you had more candidates, you'd extend it in the natural way. And so let's see what happens here. So let's just look at Johnson. So Johnson, 45% of the time gets 2 points, 40% of the time gets 3 points, and then 15% of the time gets 1 point. So Johnson's board account is 2.7, and you do the others, and here's what you get: 2.35, 2.35, 2.6. And so with board account, Johnson wins. Now, interestingly enough, there's nothing magical about 4 points, 3 points, 2 points, 1 point. Why not make it 100 points, 10 points, 1 point, and 1/10 of a point, for example? You could have other points that are assigned. Interestingly enough, with this example, we can make any of the candidates win if we assign the points in the right way. So what do we do? That's the real question. What do we do? So the question is, what method should we use for voting to really assess what is the will of the people? And there are two basic questions in doing that. One is, what information do we collect? And then the other question is, how do we combine it? And so some possibilities for the information to collect. This is what we currently do, at least in the presidential election. There's some local elections or in different organizations, like at Princeton, when we when the faculty vote to elect members for different committees, we actually use a ranked voting system. You rank the candidates. I actually don't know how they combine them, so it could be rigged, but at least we dutifully give the information of all the rankings. But we could, in presidential elections, this is all that we collect. But there are other things. So you could ask individuals to give rankings. You could ask individuals to indicate who are acceptable choices. You could give a score. It's called range voting, where you give a score from 0 to 100 to every candidate. So there are a variety of things that we could collect. And then the question is, how do we combine them? Yeah. Yes. Yeah, although what I would say is that, so by acceptable choices, and something I'm going to put a plug in for later at the end of the talk, by acceptable choices, so right now you go into a ballot and you have a bunch of candidates, say 4 candidates, and you get to pick one. There's something called approval voting where you could go in and actually pick as many as you want. So you could pick, Clinton and Johnson are okay, and leave the others. I guess that's what I meant by acceptable choice. And your point is a good one. Although if you don't vote at all, it's like just taking you out of the pool. So you're no longer part of the information that's being collected to gather. Correct. A protest by not saying anything, yeah. So one way to look at that is if you don't go in at all, actually that's interesting, if you don't go in at all, then it's basically just reducing the number of voters, if you will, although there might be ways of combining things that if you do go in and submit a ballot, but a blank ballot, then you might want to consider blank ballots in certain ways. Yeah, right now, yes, right now it is. Yes. You actually have information, and that's true. That's true. That is true. And there are certain ways of combining the information that could take that into account. We don't currently do that, and that's actually sort of just a unique. It's sort of an interesting way with the way that we combine the ballots that leads to that. In this case. Yeah. Yes. None of the candidates are acceptable. Yeah. That's a possibility too. Yep. So there are a bunch of choices for what we might, for the information that we might gather, and then how do you combine it? There are many, many ways to combine information too. But what I've listed here are, rather than just listing different ways, there's too many different ways of combining information. What I've listed there are some desirable properties of this. And by the way, this is old work. What I'm talking about so far, it's been in social choice theory within economics and so on. But some of the desirable properties that you might want are things like voters and candidates are treated equally, that my vote counts the same as any one of your votes, and so on. There are ways to quantify that, to make sure that the outcome is independent to permutations of voters and the outcome is independent to permutations of candidates and so on. You might want this unanimity property that if everyone prefers A to B, then society, the social choice, better prefer A to B as well. You would like transitivity, that if society prefers A to B and society prefers B to C, then society ought to prefer A to C. Non-manipulable, which is what I was talking about before, strategic voting, which I'll say a bit more about later, and this property, independence of irrelevant alternatives. So in fact, I'm going to talk a little bit about these last two. So independence of irrelevant alternatives. Let's go back to the same example, and let's suppose we use plurality voting. That's the system that we've agreed we're going to use for now. Recall that Clinton wins, but what if Johnson and Stein weren't even running? If they weren't even running, the picture would look like this, and Trump would win. And so you might ask, why should irrelevant alternatives, when we add Johnson and Stein, they're not winning anyway, in some sense to the outcome of this particular case, they're irrelevant. And so why should that change the outcome? If and that's the property, independence of irrelevant alternatives, that a voting system is independent, it has independence of irrelevant alternatives if this doesn't happen. In this case, introducing Johnson-Stein, even though they're not winning, changed the outcome. And you might ask, well, is that really something we want for social preferences or not? Well, it seems that it seems like a natural thing, and it's often one that's discussed as being desirable. It's certainly desirable for individuals. So for individuals, we don't want irrelevant alternatives to affect our decisions. So there's this philosopher, Sidney Morgenbesser, and there's a story about him. I don't know if it actually happened, but it's attributed to him, that he's in a restaurant, and it's time for dessert, and the waitress comes and says, we have apple and blueberry pie. And he says, oh, I'll have apple. And then she goes away and comes back a few minutes later and says, oh, actually we have cherry too. And he says, oh, in that case, I'll have blueberry. Right? That doesn't happen for individuals. The fact that there's this irrelevant alternative cherry shouldn't make Sidney change from apple to blueberry. And it's sort of the similar thinking that for social preferences that ought not to happen either. Well, it turns out plurality is actually very poor regarding independence of irrelevant alternatives, worse than some other systems. That's one property that we might like. And in fact, there's this classic result from social choice theory in economics, Arrow's impossibility theorem, that says the only procedure that satisfies unanimity, transitivity, and independence of irrelevant alternatives is a dictatorship, where one person decides the outcome of the election. So we all agree we better have unanimity. Transitivity seems pretty good too. We ought, if A is preferred to B and B is preferred to C, A ought to be preferred to C, in which case we're going to have to give up IIA. No, oh, sorry, the unanimity property, I should say. The unanimity property means if everyone agrees that A is preferred to B, then society should prefer A to B. Yes. So that satisfies the unanimity property. Yeah.
Without Stein and Johnson in the race, all the numbers would change. But what you're talking about is taking the numbers with Johnson and Stein in the race, crossing Johnson and Stein out because they're not competitive.
Yeah.
And now seeing what this same data with them in the race shows. Is that right?
Yeah, so I think that's right. So you have two cases. Either maybe it's easier to start the other way. So let's assume we just start with two candidates and we ask everyone in society their voting preferences. In that case, we get this profile. 45% would put Clinton to Trump, 55% would put Trump to Clinton, so Trump would win. And now if we add in Johnson and Stein, all of a sudden Clinton wins. Yeah, they are. They are. But it's a property that, like I said, it's not clear, and it's actually one that's a bit controversial in voting and social choice as to whether we really even desire IIA or not. It's one that for individuals, individual preferences seems pretty clear, and that's Sydney's case, that if you prefer apple to blueberry, you're not going to change because there are other irrelevant alternatives that you're not considering. But it's actually a controversial one, whether for social choice we should desire IIA as a property. I think most people wouldn't complain if it happened to be a property, but it's not clear that we should strive for IIA as a property. Yeah.
This is the outcome you would get from the outcome you get if you had instant running.
That's right.
So if you throw in IIA, and you had the outcome decided by instant runoff, which would you rather? Which of the unanimous would you?
Oh, no, so
The procedure proposed is
yeah.
instant runoff.
Yeah, so that's a good point. So when we say IIA is satisfied, we mean for any configuration. So in a particular, so instant runoff doesn't satisfy IIA. In this particular way that the population broke down, it happens to agree. But the point is that with instant runoff, I could construct different voter profiles for which IIA would not be satisfied. But that's a good point. It's not, so these properties should hold for any set of voter profiles. So strategic voting is the other, one other property that we might like. So suppose we use plurality voting again, and suppose that voters knew the other voters' preferences, so they knew that this was the voting profile, then these folks would likely not show their true preferences. They'd probably switch their votes and say, we actually prefer Trump, then Stein, then John. Or they do something, but they put Trump at the top because they would know that by doing so, at least their outcome would be Trump instead of Clinton because they prefer Trump to Clinton. And so those 15% are incentivized to vote strategically so that Trump beats Clinton. And the question, I mean, other folks would also be incentivized to vote strategically as well. And the question is, can we design methods, voting methods that are immune to strategic voting? We don't want to incentivize individuals to not vote their true preference. It's ideal if they voted their true preference. And again, no. And there's this other theorem, later than Arrow's, this Gibbard-Satterthwaite theorem, that says every deterministic rule with 3 or more candidates satisfies at least one of the following. Again, the rule is either dictatorial. Having a dictatorship addresses a lot of these problems, but it introduces other ones. So either the rule is a dictator, either we have a dictatorship, or there's some candidate who can never win, or the rule is susceptible to strategic voting. So again, yes, at least one of these 3 must. So it could be more than one of those 3 is satisfied, but at least one of those is satisfied. So it looks like if we don't want to deal with a dictatorship and we don't want to just say a candidate's on the ballot, but no matter what the citizenry wishes, that candidate is never going to be picked. If we don't want those 2 properties, then we're stuck with strategic voting. So, how are we doing on time? So we're running out of time. Let me say very quickly the picture here. So, and it gets back to the point that you raised earlier, that the example that I gave was just one example of how voters might exhibit preferences. More generally, with M candidates, you have M factorial possible rankings. and voters could be distributed among those. And so one way to represent the voter profile, if you will, is that it's just the fraction of the population, or the number, but let's say the fraction of the population that prefers each of the m factorial rankings. And so it's basically in this m factorial dimensional space. And a voting system is really just a partition or a mapping from that space onto candidates. So you have these m factorial possible rankings, and you have certain probabilities for each one of those, which you could represent in this high dimensional space, and partitioning the space, and each partition is labeled with the candidate who wins. That's basically what a voting system is. And it's really the boundaries where funny things happen. Because if you're at a boundary or near a boundary, voters are incentivized, could be incentivized to change their vote to end up on the other side of the boundary. And so these boundaries are manipulable, if you will. Now, not all boundaries are manipulable in the sense that a voter can change in their ranking would change the outcome, but not all boundaries are strategic, because if I'm near a boundary that I could change the outcome, but I don't like that new outcome any better, in fact, I like it worse than the current outcome, I'm not incentivized to vote strategically. So even though I could change the outcome, I won't change the outcome. And so only some boundaries are strategic. And the question is, are some methods less susceptible to strategic voting? And it turns out, yes, in a categorical way, that what so-called Condorcet methods, they're more resistant to strategic voting in a way that we can quantify. And these so-called Condorcet methods are ones that picks the candidate that wins all pairwise matchups. And that doesn't always happen. And if that doesn't happen, there are ways, you have to find a way to pick a winner if no one wins pairwise outcomes. But just to show what that means in this example, if we took any two candidates at a time, Clinton versus Stein, Clinton versus Johnson, and so on, look at all pairwise matchups, it turns out that Johnson, head-to-head against anyone, will win. And so Johnson is the Condorcet winner in this case. There does exist a Condorcet winner, and Johnson is that winner. And it turns out that what we've done is looked at certain probability models and tried to assess different voting schemes, which methods are more likely to be near strategic boundaries than others. And it turns out that Condorcet methods are less resistant. And you can show some results theoretically under certain probability models, and we actually took some data. And we gathered data, and it's a small amount of data. There is one data set that we looked at, and we also gathered data in the 2012 election, just put an online poll, got people's rankings, and actually looked at some of these things. And Condorcet methods do perform better. And most of the time, actually, you're in a region where there is a Condorcet winner. Only when the profiles fall in there is there not a Condorcet winner. So Condorcet methods actually seem quite good, but there is bad news. The bad news is that for Condorcet methods, you need rank information. You only have a method, it only selects a winner if there is a Condorcet winner, and if there isn't one, you need a way to break ties. And the problem is it's hard to compute and it's hard to understand. Can you imagine telling the electorate that what we're going to do is you pick a ranking and we're going to pick a Condorcet winner if there is one, and in fact the way we're going to do it is use this Kemeny-Young method, which it's... Yes, Google it. So so while it has a lot of properties, it doesn't seem particularly practical. So here's where I'm going to end with a plug for approval voting, which is where we started, related to the comment that you made before, where wouldn't it be nice if you could go into the ballot box and vote for as many candidates as you wanted and that you approve of? And It's easy to understand. It's easy to implement at the ballot box. All we do is let people pick more than one. You don't throw out so-called spoiled ballots, so there are fewer spoiled ballots. It's very easy to compute. It gives actually much more weight to third-party candidates. In fact, the way we do it, plurality voting, effectively there's something called Duverger's law, which effectively leads to a two-party system. And it is less susceptible to strategic voting than some other methods. It does have some disadvantages. No voting method is perfect, and there are some disadvantages. So where do we go from here? I don't know, except I think we have more work to do in understanding these various voting methods. I think tools for machine learning, statistical inference, the information sciences, broadly speaking, can actually shed a lot of light on these questions. But there's always a trade-off. And I think actually now with where we are computationally and in terms of amount of data, we're actually at a place where we can do a lot more in terms of voting, both understanding the properties of voting and thinking about different ways of voting that would have just been impractical in previous eras. I don't need to go through the summary, so let me stop there and just say thanks.
Thank you. Now, since we had questions throughout the talk, and in the interest of time, why don't I sort of end by presenting to our distinguished lecturer a small token of our appreciation for his talk. I'll just read what's written on this plaque. Presented to Sanjeev Kulkarni in appreciation for your Information Science and Technology Center, ISTEC, Distinguished Lecturer, Colorado State University, October 24th, 2016.
Thanks.
Thank you. We are adjourned.
Yeah. Thanks again for coming, and thanks for the invitation.
Oh, quick announcement. There's a second talk by Professor Kulkarni at 3 p.m. today. Laurie Student Center.